Every winter, the same deception repeats itself inside your house. You spent money insulating the walls. You covered that insulation with drywall. Month after month, you keep paying to warm the air trapped behind those surfaces. But by around 3 a.m., after the furnace has stayed silent for nearly 4 hours, the temperature drops again. The walls return nothing. They hold no reserve of warmth. The instant the heating system stops, they become thermally worthless. Now shift your attention to something sitting in your kitchen. A simple wine bottle made of glass. The same bottle most people toss into a recycling bin could become one of the most powerful thermal storage systems ever discovered. Not because of the glass itself, but because of what can be sealed inside it. Water. Per kilogram, water can retain 4.75 times more thermal energy than concrete. It surpasses brick, it outperforms stone, it even exceeds adobe, materials the construction industry has promoted for generations as reliable thermal mass. Across the American Southwest, throughout Mexico, and in parts of New Zealand and Australia, builders have spent decades stacking beer bottles, soda bottles, and wine bottles into thick structural walls. They filled them with water, sealed them permanently, and created homes capable of remaining warm overnight and cool through scorching days without consuming purchased energy. These structures became known as bottle walls. The science behind them has existed since the 1970s. Yet, construction schools rarely mention the concept. Contractors almost never offer it. Building suppliers avoid it completely because the raw materials are practically free, and a wall assembled from discarded bottles generates no profitable markup. Here's why these walls function so effectively and why standard building materials struggle to compete. Everything revolves around one scientific measurement: specific heat capacity. This determines how much energy a substance can absorb for every kilogram of mass before its temperature rises by 1 degree Kelvin. A higher value means the material behaves like a thermal battery, soaking up heat during daylight hours and slowly releasing it through the night. The numbers reveal the entire story. Concrete reaches about 880 joules per kilogram per degree Kelvin. Brick sits near 840 joules per kilogram per degree Kelvin. Adobe averages around 900 joules per kilogram per degree Kelvin. Stone remains close to 840 joules per kilogram per degree Kelvin. Water climbs dramatically higher at 4186 joules per kilogram per degree Kelvin. That means water stores roughly 4.75 times more heat energy than the very material surrounding most modern homes. A bottle wall packed with water is far more than an eccentric experiment. It represents a complete thermodynamic enhancement to a building's ability to capture warmth, preserve it, and release it gradually. The bottles themselves provide the structural shell. They become permanent containers for the water trapped inside. Once sealed, the system demands almost no maintenance. The liquid never evaporates. It does not decay. Its thermal characteristics remain unchanged over time. A water-filled bottle installed inside a wall during the 1970s still carries the same heat storage capability today that it possessed on the first day it was built. The origins of bottle construction stretch back much further than most people realize. Historical records show glass bottles embedded into buildings across several continents over many decades. In the American Southwest during the 1890s, bottles were often pressed into adobe walls mainly for decoration. Sunlight passing through colored glass projected stained patterns across interior spaces. Those early structures became known as bottle houses. One of the best documented examples still stands in Rhyolite. The famous bottle house there was completed in 1906 by Tom Kelly using 51,000 beer and medicine bottles fixed together with adobe mortar. But the idea evolved dramatically during the first American energy crisis of the 1970s. Builders stopped viewing bottles merely as decoration. They recognized them as tools for thermal survival. Filling those containers with water transformed ordinary waste into an enormous reservoir of stored energy, turning walls themselves into silent batteries capable of holding heat long after furnaces went dark. During the rise of the passive solar movement, experimental builders across New Mexico and Arizona began documenting something the conventional housing industry refused to acknowledge. Walls built from water-filled bottles were capable of holding indoor temperatures between 68 and 72 degrees Fahrenheit, equal to roughly 20 to 22 degrees Celsius, even while outdoor conditions collapsed to 20 degrees Fahrenheit, or negative 7 degrees Celsius, and they achieved it without any additional heating system running through the night. One of the earliest figures connected to this work was Michael Reynolds, the architect responsible for Earthship construction in Taos. In the 1970s, he released some of the first serious documentation explaining how thermal mass bottle walls functioned. His research passed peer review. Decades later, those same buildings are still standing, still delivering passive temperature control without relying on standard HVAC technology. The mainstream construction sector looked the other way. A wall assembled from recycled glass, sand, and mortar could never support a profitable supply chain. There was no expensive distribution system behind it, no lucrative contractor markup, nothing for large manufacturers to package and sell. Yet the evidence never disappeared. The bottles remain sealed inside those walls today. The water remains trapped inside them, and the thermal storage capability continues working exactly as intended. The material list is shockingly simple. Most of it costs almost nothing. First, glass containers, wine bottles, beer bottles, olive oil bottles, soda bottles. Virtually any glass bottle with a narrow neck can be used. Construction becomes easier when the diameters remain similar. If possible, collect matching sizes. The standard 750 milliliter wine bottle is considered the easiest format to handle and the most widely available. For every wall section measuring 4 by 4 foot, or approximately 1.2 by 1.2 meter, you'll need close to 50 bottles. Second, clean water. Each bottle must be filled entirely to the top before sealing. No trapped air. A solid water column stores significantly more thermal energy than a partially filled container. Third, sealing materials. Corks, caps, silicone, or epoxy all work. Every single bottle must become permanently airtight. Wine corks should be pushed firmly into place, then reinforced with a waterproof bead of epoxy or silicone around the edge. Bottles with screw tops can use the original cap followed by a ring of silicone sealant. Permanence matters. Slow leaks over years could weaken the mortar surrounding the bottles. Fourth comes the bonding material. Standard Portland cement mortar performs well. Natural cob also works effectively. Cob is a traditional blend made from clay-rich soil, sand, and straw. Besides adding more thermal mass, it is cheaper and easier for beginners to shape. Mortar fills the spaces between bottles and locks the structure together. Fifth, basic masonry tools. A trowel and a level are enough. No specialized equipment, no industrial machinery. That is the complete inventory. For a wall measuring 4 by 8 foot, equal to roughly 1.2 by 2.4 meter, the total cash expense for mortar materials usually falls between $15 and $25. The bottles themselves cost nothing. The process begins with preparation. Start gathering bottles roughly 4 to 6 weeks before construction begins. Restaurants, wine bars, and nearby households often discard dozens every week and usually hand them over for free. Organize them according to size. Keep wine bottles together. Separate beer bottles into their own groups. Uniformity across each horizontal layer makes the installation process dramatically easier. The entire wall does not require identical bottles, only consistency within each course. Every bottle must be cleaned thoroughly. Strip away every label. Old adhesive residue weakens mortar adhesion and interferes with the bond. Steel wool or a razor blade works well for removing stubborn glue. After cleaning, fill every bottle completely with ordinary tap water. Leave absolutely no empty space inside. Seal each one tightly using a cork or cap, then apply silicone or epoxy around the closure. Let the sealant harden completely before construction begins. Silicone requires a minimum of 24 hours. Epoxy should cure for at least 48 hours. If the seal is not hardened properly, moisture can leak into wet mortar and compromise the structural connection. The next stage focuses on the foundation. A bottle wall requires a stable and perfectly level base. For a freestanding interior thermal mass wall, commonly used in passive solar retrofits, builders usually pour a 4-inch concrete pad, roughly 10 centimeter thick, or create a base from standard concrete blocks. Precision matters here. The entire foundation must remain level from end to end. A spirit level should be used across the full length before construction continues. When integrating the system into an existing exterior wall cavity, all previous insulation must first be removed. The framing also needs inspection to confirm the structure remains strong enough before any bottle installation begins. The next phase begins with the mortar itself. If the mixture is wrong, the entire wall weakens. For standard Portland cement mortar, combine 1 portion of Portland cement with 3 portions of clean sand. Then slowly introduce water until the texture becomes thick and smooth, similar to peanut butter. The mix should keep its shape when pressed with a thumb, yet remain soft enough to avoid cracking under pressure. Builders using cob follow a different ratio. Blend roughly 1 part clay-rich soil with 2 parts sharp sand. Add enough water to create the same dense consistency. For reinforcement, toss in a handful of chopped straw for every bucket. The fibers strengthen the mixture and reduce separation as it dries. Only prepare what can be used within 30 minutes. Once mortar starts curing inside the bucket, adding more water will not restore its original strength. At that point, the chemical reaction has already begun. Now the real structure rises. Spread a mortar layer measuring roughly 1 inch or 2.5 centimeter across the base foundation. Then position the first horizontal row of bottles. Every neck must face the same direction, either completely left or completely right. This orientation is the traditional layout used in bottle wall construction. Each bottleneck rests against the wider base of the next bottle. Push every bottle firmly into the mortar bed. Twist it slightly while pressing downward to guarantee complete contact between the glass and the mortar beneath it. Before the mixture hardens, check the entire course with a level. Any uneven section must be corrected immediately. Lower bottles can be adjusted by applying additional mortar underneath. Precision matters here because errors compound as the wall climbs upward. Maintain a spacing gap between bottles of roughly 0.5 to 0.75 inch, equal to approximately 13 to 19 millimeter. Those gaps are not empty space. They become the mortar web holding the structure together under compression. Once the first course is complete, allow it to stiffen for around 45 to 60 minutes before stacking another layer above it. Then comes the upward build. Apply another 1 inch or 2.5 centimeter mortar bed over the cured row. The second layer must be offset by half the length of a bottle, using the same staggered pattern found in brick construction. This arrangement spreads structural loads evenly and eliminates long vertical seams that could weaken the wall over time. Continue layer after layer, slowly, carefully. After every 3 courses, check vertical alignment using a level against the wall surface. If the wall begins leaning, correct it immediately by increasing mortar thickness on the higher side of the next course. Small adjustments early prevent major structural problems later. Every visible cavity between bottles must be packed tightly with mortar. Those connecting bridges create the compressive strength of the wall itself. A hollow gap becomes a failure point. When construction is finished, patience becomes critical. The completed structure needs a minimum curing period of 72 hours before any finishing layer is added. At an ambient temperature of 70 degrees Fahrenheit, roughly 21 degrees Celsius, Portland cement reaches about 70% of its design strength within those first 72 hours. Full curing takes 28 days. For a polished appearance, apply a scratch coat of mortar across the entire surface first. Afterward, cover it with a final layer of smooth plaster or lime render. This creates a clean, finished wall while still leaving the bottle ends visible as both decorative details and thermal conductors. Even beneath plaster, the exposed bottle ends continue transferring heat from indoor air into the water trapped inside each container. Some builders choose the opposite approach. Instead of covering the bottles, they leave every glass surface exposed and simply finish the joints neatly. This produces the classic Southwest bottle house appearance, bold, unconventional, and visually unforgettable. But the real power of this wall reveals itself after sunset. Throughout the day, sunlight entering south-facing windows gradually raises indoor temperatures. Warm air spreads across the room. At the same time, the water trapped inside every bottle begins absorbing that energy silently. Each single degree of rising water temperature stores 4,186 joules of energy that would otherwise drift uselessly through cracks, windows, and poorly insulated surfaces during the night. A standard wall section measuring 4 by 8 foot, roughly 1.2 by 2.4 meter, using 50 standard 750 milliliter wine bottles, contains approximately 37.5 liter of water. If the daily temperature swing reaches 20 degrees Fahrenheit, equal to around 11 degrees Celsius, moving from a daytime high of 72 degrees Fahrenheit, or 22 degrees Celsius, down to a nighttime low of 52 degrees Fahrenheit, or 11 degrees Celsius, that wall can absorb and release nearly 3,480 BTU of thermal energy. To understand the scale, compare it to electricity. A standard 1,500 watt space heater operating for 1 hour produces around 5,118 BTU. That means the bottle wall quietly stores and returns the equivalent of almost 40 minutes of electric heater output every single day. No fuel, no moving parts, no operating cost. Just physics working silently inside the walls of a home. The industry ignored it for decades, but the science never stopped working. If this changed the way you think about heat, energy, and the walls around you, keep listening, because some of the most powerful building technologies in history were never abandoned because they failed. They were abandoned because nobody could profit enough from them. Thanks for watching. See you in the next one.